Okay, so that's for how we would represent every data point with one vector, meaning we take the original data and we map it down to one-dimensional space. So we can represent every data point now with one number. It's the amount that we have to multiply q by to get it as close to the original data as possible. However, PCA in general doesn't just consider one eigenvector and one eigenvalue, meaning that it doesn't map the data to one-dimensional space. It often will consider k eigenvectors, where k is arbitrary. So we want to find k vectors in order to do this. And so now the problem becomes this, like this, where we want to approximate xi by a linear combination of k different vectors, where each vector has unit length. So the dot product of any of those vectors with itself, so when k equals k prime, is equal to 1. And also those vectors have to be orthogonal to each other. So qk times qk prime has to equal 0 if k does not equal k prime. So we have these two constraints, that we now get k vectors, q1 through qk, and they're all unit length and they're all orthogonal to each other, meaning that their dot products equal 0 across different vectors. And so again, if we want to represent our approximation of xi as a linear combination of these k different vectors, we take each eigenvector, qk, and we stretch it by the dot product of the point xi with the eigenvector. So this is the amount, this dot product again is the amount that we have to stretch qk by to get that individual vector as close to xi as possible. And now, because each of these q's are orthogonal to each other, we treat it as k different approximations and then sum each of those up. So we're trying to approximate the data with a k-dimensional vector, which is the k dimensions that we get from the k different dot products here. Okay, so we want to minimize this now over q, over capital K different vectors for q. And again, we follow exactly the same procedure and multiply this all out. And because of this constraint on the vectors, we get some nice cancellations that give us this problem. So we want to now minimize this term, which is exactly as before, minus, and now notice that we have a sum over k different vectors this time. Before we had one vector, so there was no sum. Now we sum the k different vectors, and we have again exactly the same matrix product here as before, and exactly the same vector matrix product here, but now we have k of them that we sum up. And so if we want to now minimize this, we can again, of course, maximize this over the k vectors q subject to these two constraints. And now these vectors, these k different vectors, give us a k-dimensional representation of our data. So now we've taken the original data and reduced the number of dimensions to k, where the projection that we get of the data from the higher dimension is simply represented by taking the dot products of the data with each of these vectors q. So again, x can be a very high dimensional vector. We learn k of these eigenvectors. We then take the dot product of x with each of those k eigenvectors, and those k dot products give us the k-dimensional representation of x. So now we've got x in d dimensions. We represent it in k dimensions in this way. So this is our new coordinate representation for any vector x. And of course, if we want to know how this projection relates to the original value, what we're saying is that our approximation of x is the dot product of x with the kth eigenvector, which gives us the amount we have to stretch that eigenvector to approximate it, summed over all of the eigenvectors. So in practice, when we do this, what we'll often do is we'll take this matrix that we get, x, take its dot product, and then call some function in the coding language we use in order to find the k largest eigenvectors as well as their associated eigenvalues, which is the value we get. The kth eigenvalue will be the value of this product for qk. Another way that we can write this eigenvalue problem is as follows. So we can mathematically equivalently say that we're trying to find a vector q and a scalar lambda such that q times this matrix product is equal to lambda times the same vector. So what we're saying is that this matrix here multiplied by q doesn't change its direction, it only stretches it by a value lambda. Also, since this matrix product is a positive semi-definite matrix, we know that there are R pairs of these things, where R is the minimum of the dimensionality and the data, number of data points, where we have all of these values are positive. These eigenvalues being positive is a result of this being a positive semi-definite matrix, and where we can get R of these different eigenvectors where each one is unit length and are orthogonal to each other. Okay, so this is something that we can say in advance about this matrix. Why is it positive semi-definite though? So it's very easy to show actually using the SVD. We've seen how any matrix X can be broken down as a product of U, S, and V transpose, where U and V transpose are orthogonal, so the columns of U are orthonormal and the rows of V transpose are orthonormal, and S is a matrix that has non-negative diagonal values. And so now if we take X times X transpose and we write it in terms of its singular value decomposition, what we have is that this product, this matrix product, is equal to U times S squared times U transpose. And so in that sense, we can find the eigenvectors and the eigenvalues of this matrix product by just taking the SVD of the original matrix. We know that the eigenvectors, so this matrix Q has the eigenvectors along its column, is equal to the matrix U that we get from this eigendecomposition. And also the ith eigenvalue is equal to the ith diagonal element of the matrix S squared. So we get the singular values, we look at the ith one, square it, that's equal to the ith eigenvalue. And of course, because it's a squared value, it's got to be greater than 0. Also, as a pre-processing step, what is typically done is that the rows of X have their mean subtracted off. So we center the data so that all of the dimensions in our data set have mean 0. And that's so that we get something like this, where we want the data to be nicely centered along the original axes, so that we can represent this data in its first principal component and its second principal component. So that's a fact that comes from the fact of these principal components having to pass through the origin. If you imagine this data set shifted very far away from the origin, it would be much harder to find such a nice representation if this were rotated a little bit. Here's another example where we have data in R3 and we want to project it to R2 using an eigendecomposition. And I've color-coded the data here to show how the mapping looks. So in the left hand part of the slide, we have data in R3. So each of these points corresponds to the three-dimensional coordinates of the original data set. When we try to find an eigendecomposition to project it into 2 dimensions, it's like finding a plane that slices through the data with as little error as possible. So we take a plane, we drop a line to the hyperplane perpendicular to it, that's our error, and we sum that squared error. That gives us, that's the thing that we're trying to minimize. And so we get something like this. If we took this 3-dimensional data and represented it in 2 dimensions, we would get something like this. And so we capture as much of the information as possible within these 2 dimensions. Notice that if we had just simply taken 2 of the original dimensions and thrown away the 3rd, we couldn't have gotten as nice of a representation of the data set. So it's like trying to shift and rotate the data around so that we can just throw away some of the dimensions but keep the remaining, but where we align the information as much as possible along the dimensions that we're going to keep. And here's one more example. In this example, we have 16 by 16 images of handwritten digits, 3s. And so the data is now 256 dimensional. However, we don't think that 256 numbers are necessarily required to keep all of the information, all of the important information about each of these 3s. And so we project them into a lower dimension using the eigen decomposition, the PCA. And so here's what we get from the data set. Here's first the mean that we subtract off. So we take this number and subtract this vector or image from every image of a 3. And then here's the first eigenvector that we get. So we take each of these 3s, we make them into a 256-dimensional vector, stack them into a matrix X, learn the first however many eigenvectors of that matrix, and then each eigenvector can be represented as an image. Each eigenvector is 256 dimensions. We then put that back into the 16 by 16 matrix and show it as an image, and we get something like this. So here's the first eigenvector we learn. This captures most of the information. The second, the third, and this captures decreasing amounts of whatever information is left and not captured by the previous eigenvectors. So if we took this image and dot multiplied it with any other image here and summed it up, it would equal 0. And if we took each of these images and dot multiplied it by itself and summed it up, it would equal 1. And so now we have an image that comes in at 16 by 16, and we want to project it into a few dimensions. What we do first is we subtract off the mean from it. We then take the remaining mean subtracted image and dot multiply it by each of these and sum up the results. And we can get now 4 numbers, which is the result of that corresponding dot product of each of these images with the image that just came in. And now if we want to reconstruct the image, we take the dot product of our mean subtracted image, we then multiply it by the eigenvector, and now that's the approximation, like we've discussed previously, of the original image in that dimension only. And we sum them up, and we get something that looks like this. So here's the original image. If we want to represent that only in one vector, we would represent it in the mean. So that's this term here. But now if we want to represent it with one mean vector and 9 eigenvectors, meaning we learn 9 of these things from the original data, and now we take this image, we subtract off its mean, we take the result, dot multiply it by each of these images and sum up the results to get 9 numbers, and then we take the numbers associated with this dot product, multiply it by this image, and sum it with the same things for each of the remaining 9 images, we would get something like this. So this image is a 10-dimensional, or really a 9-dimensional representation of this original 256-dimensional representation of the 3. And you can see by the time we get to 49 eigenvectors, we're very close. By the time we get to 249, so there's only 7 remaining, we're almost identical, and the remaining ones would pick up on this noise here. And so here's what I've been saying. We're representing this image, x, as being approximately equal to the mean, plus the dot product of x with each eigenvector, and then we scale the eigenvector and sum it up. This is the approximation that we're making.